In this video, I'm going to show you how to do node voltage analysis with what we call supernodes. Consider a circuit like this. Typically, we'd want to choose the ground that has the maximum number of connected voltage sources. So I'll just go ahead and number them so we can see what we're talking about here. You could choose A or B or D or C. Each node is connected to at most one voltage source, so neither is more advantageous than the other. So let's just pick ground to be node D. So immediately we can say VD is 0, VC is 4, but it looks like we have nodes A and B as two unknowns. There's two unknown extraordinary node voltages. What we'll see is that they're not independent. So whenever you have two extraordinary nodes connected by a voltage source, like A and B, we form what we call a supernode. So that supernode includes both nodes. A supernode is two extraordinary non-reference nodes connected by a voltage source. So to analyze a circuit with supernodes, we do the following. We first pick a ground. Second, we identify all extraordinary nodes and all supernodes after we've picked our ground. So let's say, for example, that we have M supernodes and N total extraordinary nodes. So we're going to write KCL equations for each supernode and any remaining extraordinary nodes. Then we're going to write a supernode relationship. So let's briefly mention what this supernode relationship is. The supernode relationship is based on the voltage source connecting two extraordinary nodes. So here we have one voltage source connecting nodes A and B, which form our supernode. So the supernode relationship then is that VB is 2 volts higher than VA. So we can write those out. And for a set of n unknown nodal voltages and m supernodes, we actually only have n minus m dependent extraordinary node equations. And we solve for any desired parameters. So like in this circuit, I'm asking for IS. So let's apply this procedure, right? So you can see that there are two extraordinary node voltages that we don't know. So we'll say here n equals 2. And that leaves us with only one independent variable. So let's see how that works mathematically. Okay, so we have this supernode that I've circled in blue. Let's do a KCL equation. We only have one supernode. There are no remaining extraordinary nodes that are non-reference. So let's identify the currents leaving. I have 4 currents leaving, I1 through I4. No other currents are leaving that supernode. I'll just point out that I could identify some other currents internal to the supernode, like for example, Ix and Iy are not equal to I1 or I2 or I3 or I4, but they're not leaving the supernode, so they don't get included in our KCL equation. We then need to write our currents using known current values or resistances and voltages. So we can recognize that I1 is negative 3 amps. I2 is VA minus 0 over 2 ohms, so we'll just put VA over 2. I3 is VB over 1. And then I4 is VB minus 4 volts over 2 ohms. And all that has to sum to 0. Now, we've already written our supernode relation up here. So now we're going to substitute in so that we can eliminate VB. And now we have, as you can see, only one independent voltage, and one equation is enough to solve for this. We can push the constants to the right-hand side of the equation. So this gets me a 2 minus 4 is negative 2, divided by 2 is a negative 1. We have a 2 here and a negative 3. Gathering terms in VA, we should have a total of 2 times VA, and then we should have 2 on the other side. That leads us to VA equals 1 volt. Before we go on, we just want to double check that. So we're saying that this is 1 volt. The voltage source then makes that this be 3 volts. And that means we have 1/2 amp coming down this way. We have 3 amps coming down this way. And then we have 3 minus 4 divided by 2, so that's negative 1/2 amps going this way. And then if you add that up, well, considering that this is negative 3 amps, you can see, okay, negative 3 amps and 3 amps cancels to 0, and 1/2 and negative 1/2 cancels to 0. So we have a total outflux of current of 0 amps from the supernode, and that's a valid KCL equation for our supernode. So that is excellent. Everything passes our dummy check, and now we can solve for the unknown parameter IS, right? Because this current going rightward is the opposite of IS, therefore IS is the opposite of negative 1/2 amps, 1/2 amps. Okay, so that's an example of a simple one supernode circuit. There is an alternate solution. We could use our supernode equation and our KCL equation for the supernode. And I'll reorder this a little bit. Now we can write a system of equations. And I'm going to call this A, and I'm going to call this B, right? I can't really call this like an I, for example, because this has units of volts and this has units of amps. This came from here and this came from here. Nonetheless, I can still solve this as a matrix equation, and when I do that math, I'm going to get the same answer as before in units of volts. Now you can see that that's the exact same result as we got above, so we could be satisfied with this. So now I've shown you two approaches, one using this sort of more formal node voltage analysis technique, and then an alternate approach that really treated the KCL equation for the supernode and the supernode voltage equation on equal footing, and then instead of having one equation and one unknown, as in the previous case, we had two equations and two unknowns, and then we just solved for them using linear algebra. I hope you found that helpful. Please remember to like the video, subscribe to the channel, share it,